By now, you've seen linear regression and gradient descent, and using the equations we worked out earlier for gradient descent, you should be able to implement linear regression. But it turns out that rather than just implementing those formulas, you can sometimes get a much simpler and more efficient implementation if you use something called a vectorized implementation. In particular, the way we do this is usually using either a language with a built-in matrix or linear algebra library, so this includes languages like MATLAB, Octave, or Python with NumPy, or if you use a language like Java, C, C++, but use a linear algebra library together with those languages. And in this video, we'll show how to come up with these vectorized implementations that allow you to take advantage of the built-in power of often what are highly optimized and very well designed linear algebra or matrix vector libraries. And in particular, by using these vectorized implementations, we'll enjoy, I think, two main benefits. One is that of a simpler implementation, so that you need to write less code, and your code is more likely to be bug-free, just because fewer lines of code and easier and quicker to implement. And the second benefit is that often your vectorized implementation will be more efficient because you can use these built-in, highly optimized libraries. It turns out, so let me say what I mean by vectorization, and the running theme will be to use matrix vector operations wherever we can to replace what would otherwise be for loops, but be a bunch of for loops that we have to implement ourselves. So let me give you an example to tell you what I mean. And it turns out we've already seen one example of vectorization. So we started off defining our hypothesis as follows, as the sum over j of theta j xj. And we said that if you think of theta as a vector, and if you think of x as also a vector, then your hypothesis can more simply be written theta transpose x. And what you can do is, rather than writing your own for loop to carry out this sum, right, what you can do is instead use a built-in linear algebra library to implement this theta transpose x operation, and sometimes this will be much more efficient. Here's a concrete example. This is my MATLAB code for implementing that calculation that you saw just now, for computing the value of your prediction, sum over j, what's that, theta j times xj, right? And so if you were to use an unvectorized implementation, this is what you get. You set prediction equals 0.0, and then loop over the values of j, or I guess in the math we wrote j equals 0 to n, but in MATLAB, this is actually MATLAB or Octave code. You sum over, this is a for loop for j equals 1 through n plus 1, prediction equals prediction plus this thing over here. In contrast, if you're using MATLAB, you can just write this one statement, prediction equals theta prime times x, where it turns out in MATLAB, theta prime is the notation for theta transpose. So this prime thing, right, is how you get the transpose of your vector of theta. And so using this, you can use MATLAB's built-in linear algebra library to calculate this inner product for you. Oh, and by the way, depending on if you're doing this in C++, then you may end up writing something like prediction equals theta dot transpose times x semicolon. And so this would be maybe typical C++ implementation instead, if you had a linear algebra library that lets you take the transpose of theta by doing theta dot transpose. But I'm going to use the MATLAB example here. Okay, and by doing this, you can get a much more efficient and much simpler implementation where you have just one simple line of code instead of multiple lines of code like we had above. Now, I'd like you to try a vectorization example, and I'd like you to try to derive a vectorized implementation of something. So here's what I want you to do. Suppose you have three vector valued random variables, u, which is a vector, or really an array of three elements, v and w similarly, And suppose that you have a piece of MATLAB or Octave code that does this. For j equals 1 to 3, u of that j equals 2 times v of j plus 5 times w of j. How would you take this code and vectorize it? Here are 4 options. One way to do this question is if you look at the for loop, and if you can think, just what would you do to vectorize this? Can you come up with a simpler implementation of this for loop? That would be one way to vectorize it. Another way to vectorize it would be to look at these different answers and ask for each of these answers, if I were to implement this line of code, or this line of code, or this line of code, would one of these lines of code give me the same effect as this for loop over here? So hopefully you got that the right answer is this second choice over here. And to see that, if you think of this as performing the calculation, u equals 2v plus 5w, right? Then if you do this, then automatically you have that u1 will be equal to 2v1 plus 5w1, u2 equals 2v2 plus 5w2, and similarly for u3. And that's what this for loop was doing, right? It was setting u1, u2, u3 separately as follows. Whereas with a vectorized implementation, you just implement this one line of code and get the same effect. Now, let's take this idea of vectorization and apply it to gradient descent. Here's our gradient descent update, where this is the same formula that we've been writing down all along. This is where this term over here that I'm underlining, that's the partial derivative of my cost function j of theta with respect to theta j. And we were always saying that we would carry out this update for all j, right? And this means carry out this update for j equals 0, 1, 2, up to n. And so usually we would wrap this statement inside a for loop that says, for j equals 0, 1, up to n, carry out this update. And so we would like to vectorize this. Let me actually take this for loop and unwrap it, right? So this is what the for loop is doing. It's really saying for j equals 0, 1, and 2. So for this example, I'm assuming that h of x equals theta 0, x0 plus theta 1, x1 plus theta 2, x2. Okay, so if n equals 2, so I have 2 features, I'm unwrapping this for loop into these 3 statements down here. And as usual, we want to carry out these updates simultaneously, right? So let me just write that down, simultaneous update. And by that I mean I'm going to compute the right-hand sides for theta 0, theta 1, theta 2, and then I'm going to update theta 0, theta 1, theta 2 simultaneously. Let's see if we can come up with a vectorized implementation of this. Let me copy these equations onto the next slide, but I'll just make it a bit smaller so I have more space. Here's how we can come up with a vectorized implementation, which is I'm going to treat theta as a vector, and I'm going to update theta as theta minus alpha, my learning rate, times some update lowercase delta, that's the lowercase Greek symbol delta, where I'll just tell you what delta should be. Delta is going to be 1 over m sum of this times xi. Okay, so let's take these equations and unwrap them a little bit. So just to remind you, right, in this view, I'm going to treat theta as a vector. So theta is going to be a vector, theta 0, theta 1, theta 2. And similarly, xi is going to be a vector. So there's x0i, this is always equal to 1, x1i, maybe the size of the house, and x2i, which is the number of bedrooms in house I in my training set. Okay, and so let's pause this a little bit more, right? Theta here is going to be a vector, Rn plus 1, and n is 2 if I have 2 features. Alpha is going to be a real number, and delta is going to be Rn plus 1. It turns out this is what my definition of delta is going to be. And so delta is 1 over m, sum from m equals 1 to m of this thing, where, again, just unwrap this. This thing here is a real number, and this xi is a vector, Rn plus 1. So I hope this let's see, let's change colors. I hope this summation notation makes sense, right? So this is a sum of a real number times a vector. So by analogy, in the previous example that you worked out, right, we saw that we had 2vj plus 5 wj, right? And then eventually we did this for all j, and then we vectorized this as 2v, or we had the update, I guess, u equals 2v plus 5w. Okay, and so this example is a little bit like that, where we have a vector gets updated as a real number times a vector plus a real number times a vector. And that's what this summation is really. Well, let me take this summation and write down a couple terms of it. This is going to be, the first term is going to h subscript theta x1 minus y1 times x1, and then plus x2 minus y times x2 plus, and so on. Okay, when we're summing over this index I. And so just as you had real number times a vector plus a real number times a vector, this is a real number, right? That's the error you make on training example 1, times a vector, that's the feature vector of training example 1, then plus a real number, that's the error you make on training example 2. That's the difference between what your hypothesis outputs and what was the actual price of a house, say, times x2, which is the features for your training examples, and then so on, and up to, and you carry out this sum up to example m. Okay, and so hope that makes sense. That's what this summation notation is doing, is summing over your training set, summing over your entire training set of this term over here. And hopefully you can convince yourself that with this update, that, right, if delta is defined as follows, if delta is defined using this equation over here, and if I update theta as theta minus alpha times delta, then what delta is doing is is taking all of these things and is compressing them into a vector, so that when you perform this one update, theta gets updated as theta minus alpha times delta. That has the effect of updating theta 0, theta 1, theta 2, and so on, all at the same time. Okay? Just because so clear, if you look at this term, for instance, if you look at the first element of this update, right, you have theta 0 gets updated as theta 0 minus alpha times delta 0. And if you look at this definition of delta, you should prove to yourself that delta 0 is actually equal to 1 over m, sum from I equals 1 to m, this thing, minus yi times xi 0. And this thing I've written out in magenta, that's exactly this thing that I've circled up here. And so this is maybe a proof or a verification that, if I use this vectorized implementation, my update for theta 0 is the same as this, and it turns out my update for theta 1 and theta 2 are also the same as these. Okay? And so this explains how you would come up with the vectorized implementation for linear regression. Namely, for each iteration of gradient descent, you would compute this value of delta. I draw the cyan box around, this light blue cyan box around. So you compute this vector delta, and then you update theta using this formula, and that does exactly the same thing as this non-vectorized implementation up there. When you go and implement linear regression, I definitely encourage you to use a language that has a linear algebra library, and this obviously includes MATLAB, Octave, and Python with NumPy. Or if you use Java, C, or C++, definitely encourage you to find a linear algebra library and use that. And by using the vectorized implementation like this, you hopefully get a much simpler implementation that's easier to implement and more easily to implement without any bugs. And this implementation may also be more efficient, depending on your linear algebra library, maybe more efficient than what you could get if you were to write your own for loop to update these different values of theta separately.